Good. Thank you for waiting. First of all, as a Haskell programmer, I must apologize to all OCaml fans in the audience. My OCaml code will surely fail to show off the beauty of your preferred language. As a Haskell programmer, when I see the keyword let in column 0, I start to panic, and everything just goes downhill from there. But anyway, hopefully we'll still see something interesting here. So, as a Haskell fan, I'm a big fan of monad generic programming and applicative generic programming and related things. And the barrier that you hit when you're talking about most programming languages is that it doesn't support higher kinds barrier. So there's a sort of facile dismissal of the ability to do monad generic programming in any particular programming language, which is to say, language doesn't support higher kinds. And that does apply to ML. Well, maybe. We'll see how this goes. Specifically, when I talk about higher kinds, I'm talking about the sort of easy presence of a few, well, let's see what you think of this. So here's our simple type constructor. Simple type constructor maybe has kind star to star. We've got a type of values to a type of values. When we talk about higher kinds, though, we take one of these non-star constructs, star to star, for example, and we put it into an argument position. So here, the definition of maybe t, this is a type constructor that takes a type constructor as a type parameter. And you can see that in the kind on the bottom line there, star to star in parentheses. Specifically, when we're getting into monad generic programming, well, we see that with the kind of the class monad. So a simple type class over ordinary value types has kind star to constraint, whereas a higher kinded type class, like monad, has kind star to star to constraint, again, putting a type constructor in an argument position. And finally, we can use that to define monad generic functions. So in this case, it's kind of implicit because in Haskell, as in all of the languages at this conference, you don't have to declare the type parameters to your generic functions. In this case, there is an implicit type constructor generic parameter. Again, a star to star kinded type appearing in an argument position. This definition is idiosyncratic for 2 reasons. I'm not going to talk about what those are right now. So let's look at OCaml instead. And we're not going to look at any Haskell code for the remainder of this talk. So enjoy my somewhat ugly OCaml code, hopefully. So simple definitions of over type parameters are like the first line there. So this is a type constructor with 2 type parameters. In terms of the kinds we've just seen, both of these type parameters are of kind star. The returned type is, of course, of kind star as well. So it is a simple non-higher kinded type constructor. And we can see if we naively translate the maybe t type constructor that was written in Haskell earlier, well, we just get a syntax error. We don't get a kind error. We don't get anything fancy. It's just not valid syntax. So it would seem, then, that there's no way to do abstracting functions over monads. But this is what I want to be clear about. I'm not talking about implementing higher kinds in OCaml. That's not my goal here. That's not the practical goal. That's not what we're complaining about when we try to work in these other languages, writing monad generic code, and we can't do it. We're not complaining about the lack of higher kinds. We're complaining about the inability to write monad generic code, which is just so useful. So the thing we're trying to do is abstract functions over monads. So let's step back from just higher kinds and thinking about those? Well, maybe. First of all, one qualifier about what I'm going to show you is I want to say that there are no casts in what I'm going to show you. I think this is an important qualifier because there are supposed higher kinds in Java and such which use casts, and, well, I don't think those are worth consideration. So we're just going to proceed into 100% safe OCaml code. I don't promise that the OCaml code will be pretty looking. I promise that it will be safe and that we will indeed get monad generic functions out of it. So with the Jane Street Core library, Jane Street Core provides a module signature, monad.basic. So this we can read as the definition of an instance of monad. So we define T to be whatever monad we're talking about. And what's interesting about this is that T is a type constructor, even though it does satisfy the signature monad.basic with type quote A T equals quote A option. We also define bind and return, just as we do when we're writing instance monad in Haskell. We write this funny thing that says how to define map, and let's ignore that because it's not that interesting. Well, except in one way. If we want to get the rest of the functions out of Jane Street Core that we would usually like to use when working with monads, one easy step that we can take is to pass our monad.basic module to the functor. Sorry, I'm using the word functor in a totally different one than the first one, in a totally different way. Monad.make. Monad.make is a functor in the sense that it is a function at the module level. And it's a little bit more complicated than that, but I'll explain why that is in a moment. Make gives us, takes our bind definition and our return definition and gives us other definitions. But the important part about those definitions that it gives us when we invoke make is that the type T that occurs in the various functions that monad.make generates is equal to the type T that was in the monad.basic instance that we wrote. For example, if you look on the third to last line here, we have a map function which has reference to x.t. And when we pass option monad basic to monad.make, we will get a map function that has option filling in for x.t. So that gives us a hint as to how we can write monad generic functions, because when we look at this map function, that's actually what we're looking at. This is a monad generic function. So how do we write those? Well, we write them in sort of libraries. We can write monad generic functions in libraries, just as with Sebastian's talk earlier. We write programs, that is monad generic programs, as functors. So here we define a functor called funds, which takes a module of type monad.basic. And here we have sequence m, which is the function written in Haskell earlier, rewritten into OCaml. So now I hope you can see the first reason for the idiosyncrasies of the definition that I showed earlier, which is that in OCaml we don't have do syntax, and I haven't tried to define applicative. So this is a very old-fashioned way of writing sequence m, yet it is just as general as the sequence m that was defined in Haskell earlier. So what's interesting about functors? So the simplest way to think about functors is that they are module-level functions. But this isn't quite accurate. When we pass option monad basic to funds here, the sequence m that we get back has options substituted in for the t type parameter. So this code is written in a context that is universal over all monads. It doesn't know that it's option or whatever that it is. It's compiled generically. It's compiled using only the simple context, which is the implicit constraint that we have here written at the top line, monad.basic. So the reason that this gets substituted in is because our functors are a little bit more complicated than module level functions. An ordinary function type has two key elements. One of them is your argument type, and one of them is your result type. But the signature of a functor has three elements. It does have an argument type and also a result type, but it also has an argument variable. Now that variable represents the actual module that's being passed to this module level function. Moreover, that variable is bound in the context of the return type of the functor. So what that means concretely here, let's look at the three components here. So our argument type, if you look on the bottom 4 lines here, is monad.basic. Our return type is a module type that includes the value sequence m of type list of x.t of a, arrow x.t of list of a, in which x is bound to be the actual argument that was passed in to the functor. So that would be our third element, the x variable. That is to say, functors are, conceptually speaking, dependent functions at the module level. And it's that level of sophistication that we need for the option type to carry all the way through to our sequence m type definite, that is the type in our actual instantiated module, which it does. So, as with programs written for BioCepi, as we saw earlier, programs do need to be written as functors. And this is kind of an extra restriction, which will probably cut us off from other interesting enhancements. For example, the traverse type class in Haskell not only has a higher kind of type parameter defined for the class itself, but it also contains a higher kind of type parameter in a higher order position, a higher rank position, because it occurs for the function traverse itself. Whether we can represent that, I'm not sure, because, again, I'm a Haskell programmer, not an OCaml programmer. But there are things that seem to be a little bit too advanced for this simple schema of producing monad generic functions that we can do. Monad transformer. So monad transformer, as defined in Haskell, has a sort of implicit life. It's just a type definition that will happen to have a monad instance arise if you have a monad instance for the underlying monad. And that's great and all. But what we really mean by a monad transformer is that it produces a monad for every monad. And what I really like about monad transformers as functors in OCaml is that that relationship becomes very explicit. That is, you can read it right in the module type, in the functor type. We take a monad module M and reproduce another monad module with a type T that's dependent on the type T that we passed in with M. So we can't write type constructors that take type constructors as arguments in OCaml. But we can write modules that have type constructors and pass them to functors that expect a type constructor and might produce another type constructor that depends on the first type constructor. So we're sort of smuggling in this little piece with this larger program context. And while I don't think that necessarily meets the definition of higher kinds, there's certainly some extra verbiage that we're more or less required to write. We still get the thing that I said that we were really looking for, which is the ability, the practical ability to write monad generic functions. And that is all that I have. So if there are any questions. Yes? The question was about whether there was something that you could do better in OCaml this way than you could do in Haskell. Yes, specifically with regard to monad transformers. One of the things about working with monad transformers in Haskell is that you end up with a lot of new type layers because the shape of your type constructors must precisely line up so that so that they can sort of be split. That is, your type applications can be split in a very specific way, so that you can actually find the monad, which is why many of the monad transformer data type definitions that you see have this very idiosyncratic order of type arguments. So for example, for a monad transformer, you will always see m be the second to last argument. It must be there for things to work. Moreover, for every layer, you have this extra new type layers and a lot of wrapping and unwrapping the new types for monad transformers. That boilerplate does add up. With the functor representation, there are no extra layers. That is, the fact that the output t is directly related to the input t means there's no extra layer. The substitution is simply made. Now, you do have the drawback there that you have to be explicit about everything. But I think that the desire to be more explicit might just be the thing that drives people away from Haskell towards OCaml in the first place. Yes?
I've seen references to a library for OCaml called Hire. I've seen references to a library for OCaml called Hire that's supposed to simulate higher order or higher kinded polymorphism.
Mm-hmm.
Have you looked at that and compared it to this? And if you have, what are your conclusions about?
I have never looked at it, nor compared it to this.
Okay.
I should say that if there appears a single cast in that library, then I don't think it's worth considering. The cast wasn't written by Ed, who is the only one who's permitted to write unsafe coerce. Okay. There's a question back there.
Hi, yeah. How about standard ML?
Sure. This will definitely work in standard ML also. It will not work in F#, though. Yes?
With regards to implementing monad transformers as functor modules, how does the performance compare to transformers in Haskell, especially when you stack numerous ones? Or do you know how the performance compares?
I don't know how it would shape up, but I imagine that it would be similar because you don't have, so some languages don't really have new types. Or a way to do pure type level abstraction over data types. But both Haskell and OCaml do. So I imagine you would have no different trade-offs whatsoever in that area.
This might be a silly question, but did you gain any insights or changes in the way you thought about the monads themselves, like as a abstract structure from this, I guess, experiment and a different way of realizing them, or as opposed to using the type class approach?
Well, I suppose that it would be best to answer that question from a personal perspective. I'm not really sure what this tells you about the nature of monads in general. What was interesting to me about this was the revelation about the third element of functors. I actually learned about functors from Chris Martins' talk at Compose 2 years ago. And it's a very simple way to think about functors as module-level functions. And that's a great way to get started. But you have to go a level further and appreciate the dependent nature. And I think that, for me, that there's a lot of power just behind that extra dimension that I have just barely begun to perceive. There's an extra dimension of power that I've just barely begun to perceive behind that, that third element to a functor. Yes?
This is a Haskell question. Are there parameterized modules in Haskell?
The question was about whether there are parameterized modules in Haskell. The answer is no.
So this is a feature that is in OCaml and unique to OCaml then, in terms of, you were comparing the two and saying that is there things that you can express in OCaml and not Haskell? I think that was a question.
The question was about whether there were things that you could express in OCaml this way, but not in Haskell. Probably. I think that the best reference here is Okazaki. If you look in purely functional data structures, there are a lot of things that in the main text he represents using ML modules that end up getting represented using type classes if you look in the appendix at the Haskell versions of the functions. So my answer would be maybe, maybe not. You know. I think that the ability to define existential types and to erase types as you add layers or what have you you probably have much more capability to do that in ML than you do in Haskell.
We have time for one more question. I guess not.
All
Well,
right.
thank you very much, Stephen.